Welcome to EDU World Space.
Alright, so we have a y here that extends from y equal to 0 to L. We are interested in calculating the components of electric field at a particular point P. Alright, so for that we consider a small section dy along the wire that is charged, uniformly charged. Now, let's first find the electric field, small electric field due to this small cross section, that is dE is equal to K times the charge. The charge that contained in dy is lambda times dy, the charge per unit length into the length, upon the distance is r square, right? R square is x square plus y square. Now dy has two components, d cos theta along x-axis and d sin theta along y-axis. So along x-axis, dEx is equal to dE cos theta. Now cos theta in the figure from the triangle, cos theta can be written as base upon hypotenuse. So base is x and hypotenuse is root under x squared plus y squared. So what we can write, if we combine the expression for dE here, this will give me k lambda x dy upon x squared plus y squared, and this becomes 3 by 2. Alright, yeah. Now similarly, the component along dy, that is dEy, will become, with the same process, it will have sin theta in it. So that sin theta will give me y upon root under x squared plus y squared. So the expression will be k lambda y dy upon x squared plus y squared power 3 upon 2, right? So yeah, found, but since the dy is downwards, so I can write this as negative. All right, so uh, the total electric field along x-axis, so Ex is what? Ex is the integration of dEx from the whole length of the wire, 0 to L, right? So this becomes k lambda x are independent of y, so I can take them out. Sorry, yeah, I can take them out, so that becomes k lambda x outside, and 0 to L from 0 to L, an integration of x squared plus y squared power 3 upon 2, and this with respect to dy, right? Now integration of this can be seen in the appendix, and that gives me k lambda x times the integration is y upon x squared root under x squared plus y squared from 0 to L, right? So if you plug in the L and 0 here and subtract it and substitute the value for lambda, this becomes lambda L upon 4 pi epsilon naught x root over x squared plus L squared. Wow, with we are done with this now. We have calculated Ex, right? Let me keep this in a box. Okay. Now similarly we calculate Ey. Now Ey is integrating again 0 to L dEy. Now in this case only k lambda comes out, so k lambda from 0 to L, and that will be y dy upon x squared plus y squared power 3 by 2, right? Now this is equal to, if you integrate this by looking in the appendix, this turns out to be minus k lambda and minus k lambda, and this will be 1 upon root under x squared plus y squared from 0 to L, right? Right. So I missed a negative sign here. Yeah. So the next you can do is plug in the values of L and 0. This makes it lambda upon 4 pi epsilon naught, right? And if you take the LCM of the denominators and solve the fractions there, so this will be out x squared plus L squared, and on the numerator we will have x minus root under x squared plus L squared. Alright, so this is the value for Ey. Alright, now we are done with part A of the question. Now let's move on to part B. I hope I can do in this little space here part B of the question. I don't want to use the next page because I need to use the formulas Ey and Ex here. So to find that the electric field makes an angle 45 degree, let's find the electric angle first. So tan theta is equal to Ey by Ex, right? So that is equal to, if you divide Ey by Ex, we have all the denominator in common, right? So we will only have left Ey by X, only will have x minus root under x squared plus L squared upon L. So let's separate the fractions here. X by L minus root under 1 plus x by L, right? Now when length L goes to infinity, this means tan theta makes it, x by infinity is 0, so x by infinity is again 0, so that will give me minus 1. So this implies theta is equal to 45 degree downwards, right? So minus 45 degrees. So since theta is downwards, so we can write the angle that the electric field makes with the x-axis is 45 degrees downwards. Alright, so we are done with part B of the problem as well. So this was part B and this was part A as a whole. So thank you for watching. We are at the end of the